So after about half an hour or something, some of us will sneak out. You shouldn't care, and we will bring the pizzas. And then at some point, we'll try to take a little break and then continue.
Okay,
Okay? So please go ahead.
so thank you. So I wish to thank the organizers for inviting me in this wonderful program and giving me opportunity to talk. And actually, I have to do some apologizing at the beginning because this talk is prepared in some case, and it concerns something I did a couple of years ago. So last 2-3 days, I tried to revisit all these things, and on the other hand, I packed my slides with information, mostly because I don't want to forget to tell you some what is important. So the slides will be packed with information, but this is recorded, so if you want, you can revisit it slowly. Okay, so this is the work I've done in the separate works with Gordon Salvin and with Gordon Burich and by myself. So I wanted to present two different approaches to calculating exact determination of poles, location and order, and images of some degenerate Eisenstein series. I know that Erez is going to have a much more elaborate lecture about Eisenstein series, and I'm just going to present you some examples that I did with my collaborators. So, one approach in work with Gordon gives immediate information on some small representation. And in other approach, which is more combinatorial, this other approach is suited for immediate application of this information of adelic Eisenstein series to get information about some classical Eisenstein series, something that would be kind of difficult to do directly. So we had somehow different thing in mind, but when I revisited this, like in last 2-3 days, I saw that also in this other approach, because of course you are dealing with degenerate series, also some actually small representations also are lurking from behind somewhere. So just a little bit, few points why the Eisenstein series are very important. So I'm kind of embarrassed to talk about why they're important in this audience, but I have this on slides. So they are one of the few explicit means to construct automorphic forms. Of course, for example, you now have results of authors and others, Mock, Shin, Kaleta, on parametrization of automorphic representations in the spectrum of classical group and some of their in forms. But there you have some also conditions on multiplicity. So actually there is some subtle things to see if some global representation really occurs in the space of automorphic forms. And here you have, using Eisenstein series, you have the explicit appearance in a space of automorphic forms. Of course, they are also used in this work of author I mentioned. And a little bit of the history here. Degenerate Eisenstein series are also were used by Piatetsky, Shapiro, and Zales to construct the principal and function from classical groups. And also, we can use global ones to deduce the information of classical ones on GLNR, which I'm going to show you today. And there's also one other application. One can use Eisenstein series, which if they are in a discrete part of spectrum, if their images in the discrete part of spectrum, it means that all the local representations appearing are unitary. So this is one way to find some isolated representations in unitary dual of some groups. And this was the last bullet here, and it was used first, I believe, by Birgit Spitt to prove that now so-called spare representations are unitary. So the representation for GLNR. Okay, so I'm now going to talk about this first approach, joint work with Gordon Savin. So this is the situation. We have a split simple connected Chevalier group. We have Cartan subalgebra C, root system arising from this choice. We have a root spaces G alpha. So we have a set. We pick a set of simple roots, and we know that then each root can be written using simple roots like this. And we know that every simple root determines a maximal parabolic subalgebra. Actually, usually we say that all the roots, all the simple roots, but that root actually determine the parabolic subalgebra. So here in an nilpotent radical here is spanned by all the roots for which the multiplicity in which that alpha j, the simple root appears, is greater than 0. It truly appears. Okay. Now
Marcela, what's the group you would like us to think about concretely?
I will give you a table on the next slide.
Okay, fine.
So you do this with the highest root. And then you see in the expansion of the highest root, all those simple roots where the multiplicity is 1. And this will give you all those maximal parabolic subalgebras where the nilpotent radical is commutative. This is the criteria. And I want you to think about these groups. So this is the table that lists all possible pairs with one additional condition, that P has to be conjugate to the opposite parabolic by an element in G. Actually, this other condition also guarantees, when you look at this degenerate principal series I'm going to talk about, this other condition ensures, when you have a quadratic, more or less quadratic character, that all the subquotients there have a Hermitian, have some kind of Hermitian form there. Not necessarily they are unitary, not at all. Okay. So the first column is, of course, you can think of symplectic group, and this is the Ziegler parabolic situation. What are R and D? Here I will explain later. You can think of it as a GLN, GL2N, not actually GL2N, because we want these groups to be simply connected. So actually it's SL2N, but if I want to speak about Levy subgroup as blocks and everything, I will abuse say the notation and say, like in GL and GL2N you have 2 blocks, and actually all for GLN all the parabolics are nilpotent radicals are commutative, but only if you have the same block or blocks of same sign, you have this other condition satisfied. So the same for say orthogonal groups. Of course, they're actually not orthogonal, there's a spin group, so I want them to be simply connected. And we have this E7 here, and here we have also situation for spin groups. Again, I will talk about them like they are orthogonal. So SO 2n plus 3 and you get commutative and important radical if you look at the GL1 times SO2 and plus. Okay. And these are dimensions involved. So the goal is to analyze Eisenstein series. Sorry.
The condition you have with the opposite parabolic, can I also think of that in the way that the functional relation should go back to the same degenerate principal series, not to a contributor?
Yes.
So in the case of EN or BN that you have, I mean, what if you take a maximum parabolic, which is not on the outer node, but on one of the inner nodes? Where does this go to under the functional relation? So trying to understand why the other cases for BN and BN are
So they are not, I mean, you have to have a commutative. Oh, this is
okay, sorry, yes, okay. Yes.
So we want to find the poles in the right-hand plane, their order, and really to identify the more representation, their more constituents uniformly for all these groups here. And we'll do that by using Fourier-Jacobi factor, both locally and globally. And this factor enables us certain inductive arguments, even for this E7, which is an exceptional rule. Usually there are no some straightforward inductive arguments for such groups. And also this local Fourier-Jacobi factor is particularly well suited for this local degenerate principal series. So we have this commutative nilpotent radical. We can then on this space also give it a structural Jordan algebra. So some way we can also introduce multiplication. This is actually not necessary because I don't have enough time because I want to present all the other approach also. So Jordan algebra here is not strictly necessary to explain to you what is happening. So has additional structure, which is not something I'm going to talk about, strictly necessary. So what is R&D in this previous slide? So in this prototype of symplectic group, say that we are in a group case now, not the algebras. You know that unipotent radical, they are just Hermitian n by n matrices. And this R is n there in the table in the symplectic case. So R is actually the size of this Hermitian matrix. D here was 1. You see? Here D is 1 in this symplectic case. So you really have symmetric matrices over the base field. And for example, for this, let's say GLN times GLN case, you have, of course, just n by n matrices. But also, using Jacobson coordination theory, you can also interpret this n by n matrices over K as n by n Hermitian matrices over quadratic extension of small k. So somehow you see the dimensions fit. So somehow you can always, if this R is bigger than 3, we can somehow always interpret this nilpotent radical in some sense. So here you can always interpret it in somehow like certain Hermitian matrices. The other way of size R over D, and D is the field itself, a quadratic extension, quaternion of Tonian algebras, in some sense. There is another way, how can we look at this R? for Dn 2+1 and Bn+1, R is 2. And this is not, these are quadratic Jordan algebra, but not special Jordan algebra, which somehow look like this. This is a little bit different case. But another way how we can interpret R is as follows. R is the maximal, the length of the maximal sequence of orthogonal roots, mutually orthogonal roots in the unipotent radical. So there is a usual choice how we do that. So we have this mutually orthogonal roots. So you can think of them like living here in this vector space. This is a simple group, and there is only one up to a scalar inner product, which is invariant with the action with respect to the action of the wild group, and we then normalize this product. So this is the highest group beta. So as beta inner product with itself, it should be equal to 2. So with respect to this inner product, look at this orthogonal roots. So beta 1 is beta. Then you look all the roots that in N, which are orthogonal to beta, and find the highest one among them. That will be beta 2. Then you look at the orthogonal to all of them, beta 1 and beta 2, and find the highest there. And that's the way how one way how to form this sequence. And actually, this induction I'm talking about will be over this set of roots.
Are we ready to the number of orders of the living in the problem?
Sir?
Are we ready to the number of orders of the living in the problem?
No. No, not necessarily. Okay.
So is it equal to, I mean, if you take talk of Malakarta labels, I mean, maximal A1 type would be RA1.
I think that's it.
Okay.
I think that's it. And I said, I don't really need to talk about Jordan structure of Jordan algebra. Actually, for split groups, we can skip it. But if we want, we also can go through all this and have the analysis results for certain forms of these split groups from the previous slide. But I want those inner forms that somehow have the same sort of structure on Jordan algebra. And there is somehow the reverse way to think about it. There is a Fitz-Turner counter construction. I think these are the guys that a couple years ago I a little bit about all the details. And they get construction starting from the Jordan algebra, and then as a group of certain automorphism, you get to G. So you can then describe that you want all the G's for where this Jordan structure is just the inner form of this quadratic space, which you have here in a Jordan algebra. So to make a long story short, this also works for some inner forms of these split groups. So how this functions, this induction procedure. So we started with this, and we are examining this degenerate principal series with respect to this maximal parabolic subgroup, which is abelian. But we have another. Not the same matter. Another parabolic subgroup. Parabolic subgroup. Whose unipotent radical is actually the Heisenberg group. And now you somehow cut from the levy here, you intersect with M here, and you will get a smaller and smaller similar situations. So let me be more precise. So we have here a unipotent radical, which is Heisenberg root, and we denote the center D. Actually, this is the root subgroup with respect to this the highest root. Now, this is semi-simple derived group of Levy subgroup here, and has a unique simple factor G1 that is not contained in M. Then, when you intersect this G1 by M, and analogously with M, you get the maximal parabolic subgroup in G1. And this is the first step of this induction process. Because now you have a maximal parabolic with commutative unipotent radical in G1. And you can, so the unipotent radical has a Jordan structure, which is by construction, somehow this R actually tells you how many induction steps you have until you come to the smallest group, which is SL2. So actually, Jordan structure here is for this small group is you just remove here beta 1, which is the highest root.
So I'm thinking it might help. Could you show us what this means, say, for the Ziegel parabolic?
Yes. Here. So in symplectic case, you have this Ziegel parabolic, and the Heisenberg parabolic is GL1 times SP 2n minus 2. Then, so this is Q in this case. And then when you want this is G1.
L or Q?
Sorry?
The GL1 times SP 2n minus 2, the L or Q?
That's L.
L, right?
So that's the stabilizer of a null vector in my symplectic space.
Well,
Well,
yeah. Sorry.
But I always think about linear algebra. So
Okay.
with Q is, I mean, you take a vector of length 0 in there is,
Yeah.
you take the stabilizer of that.
Yes, yes.
Right. So that's the L, because there's the L is GL1 cross SP2. Yeah, 2n
Yes.
minus 2. That's the levy.
Yeah, that's the, yeah.
Yes, yes. And then when you derive it, you just get this SP2n minus 2. And this one is not complete. This is G1 actually. It's not completely in this GLN. And then you have intersect this with this, and then you have the same thing but GLN minus 1 here. And this simple situation. What is actually here very interesting? In this case, R equals 2. And you are immediately here in this case on SL2. Because here, so these are spin groups, and I'm treating that they are orthogonal, so I can write it like this. So what we have is GL1 times SO2n plus 1 with a commutative unipotent radical, And Heisenberg is G of 2 times SO 2n minus 1. Okay. And then when you look at derived, it's SL2 times something smaller, but I will again write it like this. So actually, the one which is not the part which is not contained here is this one. So you don't want a trivial intersection. This is why. So this is G1 here for you, and you're already in a very small situation. And now, what is happening? In general, we are going to introduce Fourier-Jacobi functor, which goes from smooth representation from G to the smooth representation of G1. G1 are those groups. And how we do that? So we use that we have the Heisenberg representation here on this Heisenberg group. And you can extend this Heisenberg representation on the derived group of this Levy. This is the Wave representation here. Unfortunately, if you are not in a simple late case, then you really have to use double cover here, like in a symplectic case. And then Fourier-Jacobi functor, what it does is the following. So it actually has everything to do with the nice properties of a category of representations of the Heisenberg group with a fixed central character. What is happening here is the following. So I'll put that on slide, but it's very helpful. So if we have the smooth representation sigma, smooth representation of the Heisenberg B with the central character psi, and you look actually at the category. The category of this representation, but this is isomorphic to the category of vector spaces. Namely, the Heisenberg representation is both projective and injective object in this category. So the following holds. You look at this home space, how this small Heisenberg representation embeds in sigma. Okay, then you tensor it with the Heisenberg representation. They have some independent operator here, and you actually naturally you took a vector from here and you end up here. But the nice thing is that actually this is an isomorphism. So this is some kind of old result. I don't know to whom I should attribute this, but maybe it was Stone from Hyman, I'm not sure. So somehow this is like a very nice category. So and when you start with representation phi of G, the most natural way to get a representation like this of V with a central character psi is actually to form the space of coinvariants. Okay. So one has this space, the wave representation, and this is some kind of actually this space of coinvariance is some kind of twisted Jacquet functor. So this is the vector space, but it's also a representation of G1. Because G1 acts here, as I explained, by extension of the representation, and also it's easy to see that it also acts here because G1 actually centralizes the center here. So, the mapping phi to this space is actually what we call Fourier-Jacobi function. And the nice property, which was proved by Weissman for split groups, and Gordon checked everything for all these forms, inner forms, is as follows. If you have the degenerate principal series corresponding to this pair, then when you apply Fourier-Jacobi function on this smooth representation, you actually get degenerate principal series on this model. And you get to do that until you get to SL2, where you know all about degenerate principal series, which are just principal series there. And it also gives you actually possible points of reducibility. Why? Because of the following. Okay, I will return to this, but why does it give you the information of reducibility? So, so in the Heisenberg group, this L acts on Z by conjugation and on non-trivial characters. If this action is transitive, then you can say that we can fix a non-trivial character, and then this follows. Phi is non-trivial if and only if Fourier-Jacobi function with respect to psi or that or any other psi is non-zero. This follows from this Bertin-Jolovinsky ruling lemma. So somehow Fourier-Jacobi function is exact, and it kills only trivial representation. So the important thing here is this. So from some general consideration, you know for which S's you get a trivial representation. But for all other S's, you can reason like this. So let's assume that we have S such that this is reducible. So Fourier-Jacobi, and there is no trivial representation here. Then Fourier-Jacobi, let's say it's of length n. So Fourier-Jacobi doesn't kill anything. It'll give you something of the length at least n here. So the reducibility points of these representations are among the reducibility points of this representation plus the points where the trivial representation occurs. I just want to emphasize that this actually does not mean that there is reducibility in this point. This is just candidate point for reducibility. But it turns out that you really have the reducibility, so I will just give you the results here.
Thank you, Marcela. Stop.
Maybe it's
Okay.
a good time to take a break.
Okay.
Is that okay?
Okay.
So can continue after we take a little break, start eating, and then people can bring pizzas in here and eat while you talk. And so there are pizzas.
And you should
outside.
have some too.
Okay.
We don't-
Yes.
We don't stop until
Speaker has. to
you've
eat,
had
yeah.
enough and you don't need to rush, okay?
Okay.
There is no rush. I will just pause the video for a little while. Now,
So. Let me continue.
I just asked a quick question before you go.
Yes,
So this is a local theorem, and so there's an obvious guess for a global theorem where you take Fourier Jacobi coefficient of an Eisenstein series, and then you get an Eisenstein series on a different group. Is that correct? Right.
I can read.
So no, so that is where you go. Okay, good.
Yes.
Perfect. Great.
Okay.
oh, well, maybe then I can ask you another question. So you said the p-adic situation, but you could also do this locally for the Archimedean situation as well?
Yes, and it was done by Sahi.
Oh, okay, yeah. Okay, thank you.
So.
If you can click once in the material.
Okay, okay. Mhm. Is it the same? Actually, Sahi was I'm not sure about Fourier Jacobi functor, but I know he actually completely described these degenerate principal series, how they look like in terms of K types in these situations. Did he use Fourier Jacobi functor? Actually, I don't know.
Are you talking about his papers with Dvorsky?
No,
Ah,
by
so-
him alone.
Okay.
So actually, I don't know if he used Fourier Jacobi functor or he just described
Okay.
this in some other way. So we use just Fourier Jacobi functor to have an elegant way to describe this representation. How it reduces. I'm not sure how he did it on Archimedean place. So sorry. So this is what it now boils to. So here, this is the last two cases, the last two columns, when R equals 2, so you just have 2 steps in this procedure. And you have all these situations. So you have either 1 or 2 reducibility points, because when you have from the trivial representation, if chi equals 1, so if you can have trivial representation, and then you have one additional reducibility point coming from SL2 or SL2 tilde. So these are all these cases. So for example, when you have even spin group, you have reducibility plus minus 1 plus minus n if chi equals 1, and this chi b which happens is 1, so you really have a trivial representation here. If chi is different from 1, you do not have trivial representation, you have just a reducibility here, and the similar things happens also here. And in odd case, you have reducibility in halves. So, okay, so 1 point of positive point of reducibility, or 2 of them. 1 where the trivial happens, and 1 inherited from the SL2 case, SL2 tilde case. So, but when you have a longer induction, you really have more points. And it happens that all these points, you really have a reducibility, and the length actually have a less estimate on the length of representation. It really is just. And how these are actually all the points when you can have reducibility, and how to really prove that you have reducibility. using C functions and in defining operators. You have all the candidates and you just prove that reducibility occurs. And when it occurs, it has to be linked to representation. Okay. Okay, this is Sahi's work here.
The length means the order of the flow of this function.
No, let's Jordan hold it. Okay.
So in all cases, you know the Gelfand-Karolov dimension pieces.
Actually, for the quotients which will be on the local places of the image, these are small representations.
Right.
Small.
Yeah. Our physicists are
Yes.
smiling with joy.
Yes. Okay, so the main idea is this global Fourier, applying these global Fourier Jacobi factors, and the same way how the local relates irreducible degenerate series to on bigger and a small group, you have the similar situation with Eisenstein series. So I'll just give you the notation. So we have this Heisenberg group, and X and Y are these polarizations. This is two-step nilpotent group, Z center, and these are two polarizations. And we know that we can realize Heisenberg representation and then Y representation on the short spaces X of X and X of Y, or X of Y. And so you also need theta functional. So you start from a global holomorphic section here. This global induced representation form the Eisenstein series. And you know that this convergence for a real part of S large enough. And in general, this will be notation of taking Fourier coefficients along C. Long center, and what you want to evaluate, this will be actually the global Fourier Jacobi factor. You want to evaluate this, and you see that this is pretty dark here, but this is exact the exact globalization actually of this local one. So you don't have vectors in the representation, just Eisenstein series which realize that representation, and you have Jacquet models here taken, and here you have Fourier coefficient taken. You have here com with respect to wave representation, and you integrate it here against theta series. And actually somehow when you want to unfold this, the same nice thing happened, like in that slide I skipped with a kind of geometric lemma where we actually prove this main thing with a degenerate principal series on bigger and smaller group. When you want to calculate this Eisenstein series, so you break it G as a union of double cosets. And then when you want to calculate the Fourier coefficient, only the big one, the open cell contributes. The same thing happens in a local case, so it simplifies the calculation immensely. And then when you expand it further, first of all, we also defined this expression to be a function of G1. You directly check it belongs to this smaller global principal series. And when you unfold further this result, you actually have the following. You get that this global Fourier Jacobi factor equals Eisenstein series on a smaller group attached to this F.
So F depends on the choice of additive character. Psi. F depends on the choice of additive character of psi.
Yes, everything depends on that. I mean,
Yeah.
Marcela, can I ask? So this coefficient that you're computing
Mhm.
with the theta function, how is that related to the coefficient against the center of the Heisenberg that you had on 2 slides ago? Is that,
So this thing, this is that you just integrate Eisenstein series.
yes, but can you go back 2 slides? One more, yes, no, yes. So the Eisenstein series you're calculating is this coefficient of that,
Yes.
Yes.
For this and then this.
right? So you're taking a further integral over this
Yes.
against the theta function. And so I'm just wondering like what kind of information about this coefficient do you get somehow? I'm trying to understand the role of the theta function.
But here you're just integrating against side.
No, she's integrating this coefficient against the theta function
Yes,
Later.
later,
here in 2.
yes.
I guess I wonder why.
Because we want to use Weyl representation. And
Yes,
theta is
yes.
defined through Weyl
Mhm,
representation, and we really want to globalize this local thing where the
mhm,
Weyl representation occurs. This is why we integrate here. And
mhm.
also, we like to integrate automorphic forms of the function in general.
Okay,
Okay,
yes.
so this is what we did, not caring for convergence.
Yeah, and thank you for mentioning, because that was exactly what I was just wondered. Are there any convergence issues?
Yes, yes, yes. So this works, but for real S large enough, where you have Eisenstein series converging and everything. And now what to do? You want to see where this guy, where this guy here converges. Actually, where this guy first converges. And now you write a local version of this integral, the local one. And then this is actually, this local integral is just more or less an instance of the local Fourier Jacobi, because this local integral, you also have this function here, and this thing here again goes to this local degenerate principal series here. So you just calculate locally, and you see that extend holomorphically to this region. And when you plug in all the data to be unramified, f and phi and everything, you really get just this simple L function. Nothing more. So this is local. So the product of this local factor is convergent and non-zero on this half plane. So we have an analytic continuation of this global integral also as a product of one. And also this is the remark how the sub-representations from this go to sub-representations here. You see, this can be also. Okay. So again, we have possible, now this inductive procedure gives us possible poles, but not in a way that is completely obvious, like a reducibility local situation, like we first explained. So, modulo these things I'm going to go through later. You have really possibility of poles. So totally analogous to the local situation. So the big Eisenstein integral on the bigger group is holomorphic, except possibly in this case, where this D that shows up in a transform is one, also possibly here are the possibilities for poles, and analogously in all these other cases. It just follows the reducibility. So the possible poles are almost simple. This also comes from our inductive procedure, but because in SL2 case we also have simple poles. So how to really show that if you have pole on the bigger group, Eisenstein series on a bigger group, then you have a pole on a smaller group. Well, this is how you do it. So let's say that you have a pole on a bigger group, Eisenstein series on a bigger group, so you have some kind of expansion like this. And you take F to be the vector in a residual form. That forms that will guide like this will form the residual representation. So you know that for S naught, the residual is trivial representation if K equals 1. So this is the well-known case. So assume that we are not in this situation. So let A be the residual homomorphic representation. So the thing is that you emulate, you want to prove that this actually integral, which appears here, is non-zero exactly also for these x when you take them from the residual representation. You see what is happening. Namely, if you have a residual representation and it is not trivial representation, that you can find F and G such that this coefficient is non-zero. And also using action of the finite tables and enveloped in algebra, you can shift it G to 1. And there exists phi such that this is non-zero. But if this is non-zero, when you divide it by S minus F naught on L power, this expression will really have, it will really have the pole of the of the L order. Okay, but expression you have here in this integral is nothing, is really this. So instead of epsilon factor, instead of Eisenstein series, you just plug in the residual representation, which is the highest power, the most negative power in the expansion of this Eisenstein series. So it means that this also carries this L pole here. This is what actually I was talking about here. So this also has a pole of order L. So if you have a pole on the bigger group, then you have a pole on a smaller. And now you have all these candidates for the points of pole. And now you have to really to show that the pole really occurs. And now what you do, this is standard. Oh, this is also what is happening. So the pole really happens. At each of these points, there is a square integrable and isomorphic to the cosine of the global degenerate principal series, and you really have small representation on all these places. Okay, and now what I was saying, how to really prove that you do have a pole. So this is something that we're going to also briefly review in this last third of the talk. we'll actually look at the constant term of this Eisenstein series and look at the contribution of the highest of the longest element of the variable in the constant term. And we prove that it really has a pole of order 0. And we prove that nothing cancels. So in this way, we prove that the Eisenstein series, the constant term, and then Eisenstein series itself, has a pole which is at least simple. But you know that it is at most simple. So it's simple. And also this for exceptional, it's a little bit harder to really see that there is no cancellation. But actually, this is all in all like easier case, because usually when you have a square integral residues, all these mess from other contributions of the variable is usually simpler than when you don't have a square integral residues, which will be the case in the second example. So we have here direct nice relation between local and global Fourier Jacobi functor, and we have small representation that is a residual representation. And this is application. Actually, one of these representations we actually get s equals 1, s equals 5. This is what is related to this octonion case r equals 3 on this exceptional root E7. Is this automorphic representation is actually the one discovered by Kim. Actually, he constructed, I think, a singular modular form which generates this representation. So we somehow rediscovered something which Kim discovered in a more classical sense here. Okay, and what is interesting to remember is Fourier Jacobi functor. I'm talking about a local situation, reducing the n rank by 1. So you get this bigger degenerate principal series quotient, which is of rank n but small. The next one, the one that it's an image on a smaller group, we will have n rank even smaller. This is nice property. Okay. So let me briefly just explain the other case, the other situation, which is more standard and more combinatorial, but some also interesting things appear. So this is partly a joint work with Goran. So again, I'm looking at the degenerate principal series, but for GLN. So we have two gross characters, and we have this induced global parabolic induced expectations, which is realized on a smooth and right k-finite functions from GLN plus n to C. So these are not blocks of the same size. In general, this is of size n, this is of size n.
But this is no different than from the case you described.
Yes,
Okay.
yes, it's a different situation. This is more general.
Yep.
And of course, the usual transformations will have to be obeyed. And we want to analyze where this Eisenstein series have poles and what are the images and so on. Okay, so we recall what does it mean for a pole at a certain S to be a finite order. Of course, you plot certain F's, and if the supremum or all this function is finite, then we have that finite pole. Actually, it's this infinite situations can really occur, but for in the right half plane, terrible things can appear even for GL2. So we look at S bigger than 0. So what we know is this normalized Eisenstein series, when we remove the pole, is really well-defined non-zero intertwining operator from this parabolic representation to the space of one that's this central character. Okay. So let me just see what the main results are. So what is happening in the right half plane? Well, the easy situation is if S is not among these numbers, n plus n over 2 minus alpha, when alpha is integer here. So then this is actually embedding, and the core representation gets embedded in the space of automotive. There are no. Okay. And now for interestedness, assume that these two Bronson characters are the same, so we can factor them out. So we can say that they are both trivial. So then the general principle Eisenstein series has its most simple form, and we can say the simple form really appears when alpha is equal, less than equal to n minus 1. Generally, we look at alpha like this. For bigger alphas, you don't get 4. And the image of the map is irreducible. It is the unique spherically reducible component in this representation. Okay. And what if mu is not equal to chi? Then the problem is actually we don't know much about local intertwining operators of the non-Archimedean place. So if we add additional assumption that these two characters coincide on the real place, so we can take okay that they coincide on the real place, then we can say that the degenerate Eisenstein series is homomorphic. And this is other condition that we also don't have to know what is happening in the real place, but we also have that here is orthogonal. So we have a little bit worse result when you doesn't equal to chi, because we have not enough information on our Canadian place. But for the application of classical Eisenstein series, enough is to look at the case where mu equals chi is the trivial. So we fix final place P, and we recall all these matrices appearing here. And only new thing is unipotent radical of the opposite variable itself. Okay, then what we do? We are going to construct open compact subgroup LP of L for L certain image. So this is just in ZP, in ZP, in ZP, and just P in a little bit more. So it's kind of a paraphoric subgroup here. And the determinant is in integer of module 1. And all these matrices form an open compact subgroup, and what is important, it has an Iwahori factorization. Okay, this is for some place P, we define this open compact subgroup. And then we look at the global situation. Then we